Hi everyone, thank you for joining this presentation. I'm Rajesh Yamarthi. I'm an architect at MetiStream. I'm specialized in extracting clinical data from unstructured data processed with NLP using our custom data extraction engine. I'm here to talk to you about some of the best practices in improving NLP accuracy for clinical use cases. I'm here with my co-presenter, Vaisal Kokaman from Johnston Labs. Where we closely work with JSL for leveraging NLP as part of our use cases. MetiStream is an healthcare analytics software company. Our Ember platform helps healthcare organizations to process unstructured clinical data so they can leverage their data to improve patient and population research and analytics. Ember processes large volumes of clinical data and it has a capability to run NLP on top of it. We support various sectors in healthcare. On the provider side, key use cases are for quality, clinical research, and population management. Bio and life sciences organizations can leverage our platform to accelerate drug development and to be able to identify better patient information for clinical trials. On the payer side, for quality and risk predictions. Let me give you a high-level overview of our Ember platform. Ember is an end-to-end data integration platform that integrates and correlates unstructured data. We really think about this as an end-to-end perspective because we want to help healthcare organizations to maximize their data, not just processing unstructured data, but structured information as well, and to make the process of leveraging the NLP data for end users much more simpler and easier. Ember has four main components. Has a strong data integration capability to onboard data from multiple different sources like Cerner and Epic. Has a robust NLP component, obviously working with Spark NLP. As part of the MNP component, we also have a proprietary, robust data extraction engine that complements NLP component. Ember has an ability to build predictive models using the data that has been processed with NLP. Ember Insights allows end users to build cohorts using the data that has been processed. Ember provides much more interactive way for users to use NLP data to be able to search using concept search, ontologies, and custom query. The users can also build dynamic dashboards. These are some of the NLP lessons learned and best practices I'm going to talk to you today. I'll go one by one with examples in the next slides. I'm going to use one of the solutions that we worked on recently as a use case to illustrate the challenges that we have faced and how we solve those challenges. I'm going to talk about a use case for adenoma detection rate. So what is adenoma? Adenoma is a cancerous adenomatous polyps. It is often found during colonoscopy procedure. Colon cancer is a number 2 cancer in the world. So ADR is a quality measure for colonoscopy procedure. It is typically done on patients of age more than 50 years. Lot of the key information regarding colonoscopy procedure, like number of polyps, type of polyps, can be only found in clinical documentation. We have to extract key information from unstructured data. So there are various steps involved in performing ADR calculations. NLP is a foundation step. So high NLP accuracy plays a crucial role for other steps to get more accurate ADR calculations. Most of the solutions out there very much focus on ICD-10 CM codes. Our solution use ICD-10 CM codes as well as SNOMED codes. This is a sample NLP pipeline. It's not just an NLP pipeline, it's more about various different processing steps involved for ADR calculations. So our clinical notes run NLP as a pre-processing step. It goes through sentence detection, tokenization, chunking, and resolvers. Once this pre-processing step is completed, our data extraction engine tags the ADR entities, extract DMP attributes like diagnosis, medication, and procedure. It also extracts accession information and ontology codes. So once all this data has been extracted, we perform ADR calculations. Clients can leverage this data by building predictive dashboards and making decisions. So there are different NER models in NLP. So each NER model categorizes the entities into different categories. Identify your use case and find the NER model with the categories that works for your use case. So once you find the model, test your data to capture the correct NERs and make sure you are actually capturing the correct NERs. So in this case, I'm going to talk about one of the example text, high-grade dysplasia of colon. So the model has tagged the text as two separate entities. We need to capture this as a single entity. Why is it important for us to capture high-grade dysplasia of a colon as a single entity? For a patient, if a polyp is mildly abnormal, then it is dysplasia of colon or low-grade dysplasia of colon. If a polyp is more abnormal, then it is high-grade dysplasia of colon. It is cancerous oftentimes. So the ontology codes for dysplasia of colon is different for high-grade dysplasia of colon. So these for ADR calculations, the ontology codes are very crucial. So in those situations, use greedy mode in NER converter to make it as a more clinical, to capture more clinical entity. Now I'm going to pass it to Vaisal to add more context to this scenario.
Thank you, Rajesh. This is Vaisal Kocaman from Johnson Labs. We work together on this project, and we still work together with MetiStream on their great product. So I would just want to explain how NER converter help in the use cases that Rajesh mentioned just a few seconds ago. So right now, if we can go to this slide. Yeah, in Spark NLP, like every entity coming from any RDL model comes with B and I tags. We call it bioschema, but B and I means that on the left hand side you see that like a B modifier and I modifier. It says that like the B is the beginning of the high grade entity. Like high grade is one chunk, we call it chunk. High is the first token, and since it is the starting token of high grade chunk, we call it B. So anything after comes after B is the type of the entity that is extracted by any RDL model. So the things that we see after NER models, like a name identity recognition model, all produced by B and I tags. So NER converter's job here is to take this output from the NER model in the same pipeline. So as Rajesh showed, we have a pipeline in Spark NLP. We build everything in a pipeline concept. So you just connect the output of one annotator to as an input to the another annotator. So here we basically get the output from NER as a BI text, and then NER converter creates the chunks. Like the high grade BNI becomes high grade modifier, so the text disappear, and then the dysplasia of colon becomes 3 token 1 chunk, so one entity, disorder entity. So in Spark NLP, since Spark NLP for healthcare extends everything from the open source, the NER converter is same, but in in the license version we have the NER converter internal. So NER converter internals add some more capabilities on top of NER converter. On the orange box, you see that how NER converter internal works. It basically, right in NER converter internal, you can tell the NER converter how to join these B and I tags. Okay, like in a greedy mode or not. Greedy mode means that if there are if we have two different entities like a chunks coming from NER model, and if there is any other token between them, let's say high grade is disorder and dysplepsia colon is a disorder. So in NER converter, if we use the open source version, it would just return two different chunks, as you can see on the left hand side. But when you use the greedy mode in NER converter internal, you will get the combine all of them as one single entity. So high-grade dysplasia of column become one single chunk because there is no other token between these two chunks. This is a one way of doing this. Like another way of doing this, manually changing the data set. Because all NER models are trained on CoNNL data format. On the right-hand side, you see a snapshot from a data set. Like we have all sentences are split by tokens on each line, and there's a space between each sentence. This is how we train our models. We prepare this data set at first through some other annotation tools, and then feeding into the NERDL approach to train our models. And so since we already know that like a B and I text here, if we can manually change, like instead of a BI disorder and then BII, we can just we can just merge them manually. Manually means that we can just write some code, right? And then say that if anything comes after the tag, like a B and I text are same, join back them, or remove the stoppers and then join them back. In this case, we can just hard code the CoNNL file, change, and then retrain. So we could be able to end up with the same solution that NER converter in internal does. So by using the NER converter internal, the MetiStream didn't need to do this manual CoNNL edit, and then they just because we already know that the modifiers usually comes from the comes before the disorders, and if there is no other token between them, just join them. Then this would be a much informative chunks to feed entity resolvers to extract ICD-10 CM and SNOMED code. Okay, over to you, Rajesh.
So in the next scenario, I'm going to talk about combining the modifiers. So, and the example text, multiple adenomatous polyps. Here again, multiple is a modifier. So it represents a number of modifiers, number of adenomatous polyps. So in this case, for our calculations, adenomatous polyps ontology code is completely different than multiple adenomatous polyps. So in those kind of scenarios, in order to add those modifiers to capture meaningful clinical entities, so we use a chunk merge approach. So that way you can get more accurate NER tagging as well as the resolver codes to be accurate. So here the chunk merge approach just combines those modifiers and then specify what kind of modifiers you have to merge to get it into a single entity. Yeah. Hey, Vaisal, could you please add more context to this?
Yep, sure. So apart from what we did with NER converter internal, because we were trying to merge the multiple chunks having the same labels, if there is no other token between the chunks. So we are using the same NER. Here, if assume that you have multiple NER in real world use cases, we usually build all the add all the NER models on top of each other and then connect the dots, and then we have one giant pipeline. Which means that if you are going to extract some medication, you use NER pathology, and then if you want to extract some radiological entities, you use NER radiology. Which means that you need to join them together. Since each NER model doesn't see what's coming out of the other NER model, so there might be some overlapping, right? Like on the left hand side, you see here that on the right hand side, you see recurrent infection is a problem entity. So on the right hand side, the entities comes from NER Clinical, our flagship NER model. So it has just 3 entities: problem, test, and treatment. So let's see what comes out of the second NER model, which is called NER GSL internal, our internal NER model. Here, infections are like a recurrent is a modifier, infection is a disease. So which means that I have more granularity right now. If I want to join back, like merge these two predictions coming from two different NER model, we can use chunk merger, which is not possible in the open source. So chunk merger is an annotator that we developed for the Spark NLP for healthcare library. What it does is it has two modes. So it can ignore the overlaps and list all the entities one by one coming out of the same text, but it might be very problematic because you don't want to use the same tokens again and again if they are assigned any label by different NER models. So what we do is we take this chunk merger checks which one is more informative. Like the more informative means that like the checking the entropies, like what is the longest sequence coming out of which NER model. So if you see recurrent infractions is more informative than recurrent and infractions on the left hand side, which means that other than using NER converter internal, because right now we have two NER model, so we cannot use NER converter internal to get what we need. Of course, you can apply the techniques that I just described, but in chunk merger, if you have multiple NER model, you can just join like add and NER A, NER B, and chunk merger, and then NER C, NER D, and then you can just every time you can just join like or merge the NER outputs into one single NER so that you don't have the repetitive, you don't have the duplicate token. So as an output, as you can see, recurrent infraction is a problem entity, which wasn't possible through like the first NER on the left hand side or the other NER on the right hand side. So this is how NER chunk merger works. Another approach, another option in the chunk merger, as I said, ignoring all this overlap and then list everything. It's very useful to analyze the documents, especially like some like thousands of documents, clinical notes, to see what else I can get out of this text data without checking the overlapping tokens. Just want to know how many entities appear most out of which kind of documents. So over to you, Rajesh.
Thank you, Vaisal. So in this scenario, we talk more about SNOMED ontology codes. As I said before, our solution also uses SNOMED codes. So in the example text, like multiple adenomatous polyps and tubular adenoma of colon. So when you run SNOMED resolver on these two example texts, the SNOMED code will change, depends on the concept that we use for SNOMED resolver. So SNOMED resolver has multiple concepts like clinical findings, morph abnormality, procedure, and some others, etc. So here, when you run the multiple adenomatous polyps on using just clinical findings, the SNOMED resolver code is different from when you run the same multiple adenomatous polyps on morph abnormality concept. So in those cases, you find the your use case and see what your entities are falling into which concept. So identify the concepts to get more accurate SNOMED resolver codes. Yeah, I'll pass on to Vaisal for this.
Okay, so as Rajesh just explained, we have several concepts in the SNOMED. Actually, it's not dictated by us. According to NHI, National Health Institute, like for this kind of medical terminologies, SNOMED, ICD-10, they have sub-concepts. Especially for the SNOMED, since SNOMED is a large, actually larger than ICD-10 CM, so it has some sub-concepts that we had to split into different models. On the left-hand side, you see the different variation of the resolution models that we trained and served to our customers in Spark NLP for healthcare, which means that we have different resolvers for each terminology. Like we have a specific resolver for ICD-10 CM and another for RxNOM and another for SNOMED. So we would be able to train a single model for the slim ones like ICD-10 or RxNOM or CPT. But when it comes to SNOMED, since it's like its corpora is very large, like the terminology is very rich and then cover multiple other terminologies. So, and then training a one single giant model would not be a computationally optimal solution. That's why we wanted to we used to just select the clinical findings concepts in the SNOMED software. And then we found out that MetiStream needs other concepts coming from other other terminal, other terms, other chunks coming from other concepts like morphology. So they ask us to train another model for the other concepts, sub-concepts of the SNOMED. So what we did is we used the same data set that the SNOMED has, and then we already have some in-house and rich augmented data set for SNOMED. We map it with the ICD-10 and then augmented, etc. And then we train different models. The first reason for training a different model for each sub-concept is, as I said, it's more optimal in computational aspects because you don't want to load 3 gig of model onto your memory and then just keep it there, right? Why is that big? Why these terminology or resolution models are big? Maybe Rajesh already mentioned, but what we do here in the entity resolution models in Spark NLP is that we get the chunks, like medical entities from NER model, and then feed this passing through NER converter. We have a desired chunk right now, and then now we feed this to entity resolver. Entity resolver, before entity resolver, we pass through a sentence BERT, which is a fine-tuned version of the BERT, like a fine-tuned version of the BioBERT. So it's not a word based, it's a sentence BERT embeddings. We get the embeddings of the chunk. Instead of getting the embeddings of each token and then average later on, we fit the entire chunk to the sentence BERT embeddings, and then this BERT embeddings feeds resolvers is already trained with these embeddings beforehand with these concepts and codes. So it's there is an algorithm running on behind of resolvers. We have two resolvers, by the way, in Spark NLP, which is chunk resolver and sentence resolver. For MetiStream use case, sentence resolver produce better results than the chunk resolver, so we use sentence BERT over there. So we fit this, and then it has some inside us. There is some since this is an unsupervised learning stuff, so there are some KD trees already implemented by us on the backend of this algorithm, and then it just tries to find the most similar, the most closest one according to some cosine or Euclidean distances dictated by the user. So it tries to find the most similar terms given the chunk. So since we are using BERT, this is very large model. Since large, like each chunk becomes like 768 dimension. So which means that that's the size of the trained model increased by the size of the vocabulary. So if we have larger concepts in one single model, it will be more slower and computationally hard to carry in the memory, right? So that's why we train different models for different concepts. So for the clinical findings, we trained one model. For the morphology, we trained another model. And then MetiStream just feeds their chunk to these resolvers and then check its confidence level and then the distances. We have the distance metrics over there, like a cosine distance between 0 and 1. It says how close any chunk to any concept. So if it's very close to some concepts in the clinical findings, so it's pulled. If it is not, if it's very close to concepts in the morphology model, it will be picked as a result as a SNOMED code. This wouldn't be possible if you would just use one giant model because it would crash and then you wouldn't know what's going on. That's why we applied this kind of tricks, and it helps a lot. Okay, Rajesh.
Thank you, Vaishal. Yeah, as Vaishal mentioned, like there are two SNOMED models. The same text that the text that we have to run in a single pipeline. So if we pass this multiple adenomatous polyps and tubular adenoma of colon into two different models, then how do we know which SNOMED code is the accurate one? So how to resolve this? So what we did was, so we passed through the multiple adenomatous polyps and tubular adenoma into clinical findings model, and again into morph abnormality model. So then our data extraction engine, what it does is it looks to the confidence value. See, in multiple adenomatous polyps in clinical findings, the confidence value is 0.1631. But if you see the confidence value in morph abnormality, it is way more than clinical findings. So our data extraction engine compares the confidence value and take that SNOMED code result like 6379007 for multiple adenomatous polyps. And if you see for tubular adenoma of colon, the confidence value in clinical findings is more than morph abnormality. So these comparisons will be performed, and we take the code that is more accurate in those cases. Here, if you observe, the distance is vice versa, where the confidence is less, the distance is more, and the confidence is more, the distance is less. So, as Vaisal mentioned, they are using Euclidean codes, right? So, in our data extraction engine, so we compare more of a confidence and then get the actual clean, SNOMED code, which has improved our accuracy for SNOMED results. So in the next scenario, this is a general scenario that I'm going to talk about to capture better NERs. So most of the time in PDFs have a tabular structure. So when PDF data for clinical notes is converted to text, the clinical entities may fall on different lines. In those cases, there is no clear indication for a sentence boundary. So if you see that NER, here the first tag, first entity, it has also captured type from a different line because there is no clear separation from the sentence. And with those, they are completely a different from a medical entity, right? So in those cases, you need to identify the clear boundaries to make it as to identify it as a sentence. So that in those cases, use sentence custom boundaries on sentence detector. Vaisal?
So why is sentence detection is very important? Because everything starts with NER model, right? We have been discussing this a lot. So everything starts with NER model, and NER is trained sentence-wise. So the model that we use, the algorithm that we use in NER model is called by LSTM CNN architecture. It's a sequential model and works sentence-wise. So it only sees the sentence that entity lives in. So if you don't have the right sentence, if it's corrupted due to some end of line or some OCR errors, right, you end up with garbage as a sentence. So if you feed a sentence to the NER model that the NER model hasn't seen so far due to some corruption, because the co-NL data, we create that a lot before training any NER. So if you feed a wrong sentence to the NER model, it will probably fail detecting that entities. That's why sentence detection is highly crucial while creating the proper NER chunks for any NER model. So what we did with MetiStream use case is that at first we use sentence detection pragmatic approach. We have two ways of doing this, by the way. Sentence detection DL, which is a trained version of the sentence detection, splitting the sentences given the context, and the other way is pragmatic version by using some other statistics. Okay, so we saw that there are some data coming inside the table on the MetiStream use case, and then in the table, as you might see when you wrap the text, there are some end of line. If you feed this to any sentence detection model, it will probably fail if you don't set some sentence boundaries. Since this is a known use case, since you know that the wrapping probably adding some end of line for each chunks, like after few token, there's an end of line and another token, etc. So we suggested them to use end of line as a splitter. Another rule, of course, it's also checking many other things while splitting the sentences, and then creating the sentences so that you wouldn't end up with a half sentence, and then end of line is also considered another sentence, etc. So since I want to take the opportunity here to explain the DL version of the sentence detection, as you can see, the text data in the clinical notes are usually corrupted due to some scanner error or OCR error, right? So that's why we train the model to detect the sentence boundaries in a deep learning, like after training some CNN and LSTM networks. So on the left-hand side, you see the Spark, how Spark NLP splits the sentences. And on the right-hand side, you see how Spicy handles the sentence splitting. And you can see that on the clinical version, we have a clinical version of sentence detection, by the way. You had the most optimal solution for the sentences. Okay, over to you, Rajesh.
Thank you, Vaisal. Yeah, so use this as a custom bounds on the sentence detector so that it will it will clearly identify the sentence boundaries. So you don't have you will not get not meaningful entities. So with that, it will identify the custom bounds and then capture the actual entities. Yeah. So in summary, accuracy is an iterative process. So there are two things that we have to do to improve NLP accuracy. One, identify your use cases and check if you are capturing the NER entities correctly. So if you are capturing the NER entities correctly, then look for the ontology codes that you are looking up them correctly. So we worked closely with JSL to provide feedback and test results to iteratively improve our models. So and we also made sure that what combinations of NERs works for us for our clinical use cases. So that's where we have closely worked with JSL. Vaisal, would you like to add something?
So, as you might have noticed so far, all the components in Spark NLP for healthcare library already crafted and developed according to the feedback coming from customers and lessons learned from real-world use cases. So, whenever we work with our customers, like work on a new challenging project, we end up with some boundaries that we haven't envisioned before. Then we work them together, like we work the colleagues from the other companies work together, and then try to develop an optimal solution to help them on their use case, and then this become a product for the rest of the library. So we just because we develop some modules for them, and then if we are not using their own sensitive data, if this is something that we already did just for the GSL resources, so we make it an annotator and then ship to the other customers as well. So as we did with this kind of chunk merger or NER converting, all these models are developed according to the some use cases and some feedbacks coming from customers thanks to that. Okay,
So
over to Rajesh.
yeah, so these are some of the techniques to improve NLP accuracy. So hope this helps you. Hope this will help you. Thank you so much for joining this presentation.